Okay, so please watch the algorithms video in 3.16.0. Um, we're not gonna, oh, and watch the vehicle routing problem. So a lot of these things and the computations, etc., get very, very complicated very, very fast, which is why you need programs. Um, Honestly, for a delivery system like an Amazon deliverer, they're told what to go where. If they tried to do that by hand, it would take longer for one person to calculate their route than for them to just drive it. So they've programmed things that take into account all these constraints, etc. Okay. So complex real-world problems can be modeled and solved using graph theory. Good news for you, you will not be solving anything nearly as complicated as the computers. Okay. There are a few challenging problems on this. Mostly the challenging part is remembering the algorithms. I will give you a page of notes to write down your algorithms in addition to your formula packets for next week's test. Okay. So, yes, you need to know the algorithm and what it does. Theory of knowledge. Applications of knowledge is a key feature within areas of knowledge, including mathematics. When discussing and contemplating the application, the question of ethics arises. For example, mathematical knowledge is not necessary to create weapons of math. Mathematical knowledge is necessary to create weapons of mass destruction should such mathematics be pursued and shared. Is all knowledge value neutral? Interesting question to think about. Okay, we'll discuss that more in TOK2 this year. But yes, definitely advanced math is needed for developing WMDs. But there's also other applications to that. Okay, paths and trails. You can move around a graph. We talked about walks last week. Well, now we're going to talk about a path and a trail. There are many different walks that satisfy the given conditions above. The condition says, consider the graph. Can you find a walk that begins at vertex A with at least 5 vertices in total and ends at D? And it says at least, so there's all kinds of different options that are in the at least category. They've got this, they've got this one. Notice they start at A and end at D. A path is a walk that has no repeated vertices. Okay, make sure you know that definition. So if I'm looking at these three, which ones are paths? The last one is uh A, F, B, A. No, the second one repeats A. The first one repeats A and E. So just the last one is a path. Again, lots of vocab in this part of graph theory. For the graph above, determine whether there is a path that travels from A to C and finally ends at F. Is there a path that goes from A to C to F? A path. Path has no repeated vertices. No, because you have to go through E twice. So it would look, something like A to C, but I have to go back to E to get to F. So no path. A trail is a walk with no repeated edges. Guess what? There is a trail. I drew a trail. Okay. So this is a trail that goes from A to C. Okay. No repeated edges. It does have a repeated vertex. A path can't have repeated edges because you'd repeat a vertex then too. So for the graph shown below, determine whether there is a trail from A to B that ends at D. The answer is no, because the only way to get to B is from F. And so you'd have to go back if you're going to end anywhere else. That makes sense? A cycle and a circuit. A cycle is a graph on a graph is a walk that begins and ends at the same vertex, but otherwise has no repeated vertices. The length of a cycle is the total number of included edges. So it says list all the cycles in the graph that begin at the vertex E and state their length. Cycle number 1. That's 3. Got a length of 3. Cycle number 2 also has a length of 3. Cycle number 3 has a length of 4. I don't think there's another cycle. Has to begin and end at E. So, yes, there's other cycles that start and begin in other places, but I think, let me double check what the answer says. That one's like 3, that one's like 3. Yeah, got them all. So that is a cycle. Not so bad so far, is it? It's gonna get harder in 316.2 and 316.3 and 4, I guess. It's never that bad. Okay. State a circuit on a graph is a trail that begins and ends at the same vertex. Okay, so it's a trail. A trail has no repeated edges? Yes. Yeah. You know? Yes. So the cycle had no repeated vertices, so it was a path. A circuit is a trail. Um, can also be described as a closed trail. It's another name for it. So Example 4, state a circuit in the graph that begins at F and travels through vertex C. Okay, so it begins at F, travels through vertex C. I'm going to go this way. And that's a circuit. I could have reversed my order, or there's other ways around those sides, but uh, a cycle doesn't repeat any vertices. A circuit doesn't repeat any edges. So notice that E was repeated in here. So that makes it not a circuit or not a cycle, but it is a circuit. You could also do, I guess this I think would work. So couple more definitions, and then we're on to the next section. Okay. So this graph is what we would call a disconnected graph. You cannot get from A to B, can you? So a connected graph contains a path from every vertex to every other vertex. The graph below is not a connected graph. Because of its direction, you can't get from E to C. Or really from any vertex to C. I'm not sure if that applies to any others, but I guess you can't get from E to B. You cannot go from vertex E to B on that graph.
Yeah.
So that is not a connected graph. A strongly connected graph is a directed graph that contains a path from every vertex to every other vertex. Connected graph is not necessarily directed. Now, the one that they showed you here was not connected, it is directed. Strongly connected has to be directed. Okay. Now we're going to talk about trees and what's known as a minimum spanning tree. Okay. And knowing how to create a minimum spanning tree is important for some of the other algorithms. A tree is a connected graph that contains no cycles. They usually look like what's shown in this activity box. Okay. What was the definition of connected? Hmm. And so you can get from all vertices to the other, but you can't get back without repeating vertices. So it says here, consider the three graphs. Count the number of vertices and edges on each graph. That's pretty easy. You guys can all do that. Propose a relationship between based on the patterns. What do you think the relationship between the number of edges is and the number of points of vertices? What was that, Ron? It's off by, it should be off by one. It's, so if I were going to do the first one, I should get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And edges, we should get 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's an incoming edge for every one except for the point of the tree, A. So edges is vertices minus one. Draw a few more trees. Does it continue? The answer is yes. Explain why that relationship is true. I just did that because there's an incoming edge for everything. Once upon a time in college, I proved that using mathematical induction and a couple other things on binary trees. Binary trees are trees with only two that have two off of each vertex. Exactly two. Okay. So a tree that contains n vertices is n minus one edges. A minimum spanning tree. So here we've got a graph. Imagine that the vertices in the weighted graph above represent the villages within a small region of the country. Weights of each edge represent the cost of connecting each village to the electric grid. How can the local government connect all the villages to the grid at the minimum cost? To answer this question posed above, you need to find a minimum spanning tree. A minimum spanning tree is the following. It's a subgraph of adjacent weighted graph that has the following three attributes. It's the subgraph with the lowest weight. It connects all the vertices in the graph. It does not include any cycles. So no cycles makes it a tree. Yep. Looking at what's coming next. There's a couple of different algorithms for this. There's Kruskal's and there's Prim's. We'll start with Kruskal's. We'll look at some exam tips, and then we'll look at Prim's, and we'll learn how to do it with adjacency tables and matrices, and let your calculator do all the calculating for you. because the matrix operations would be nasty if you tried to do them by hand. So, demonstrating Kruskal's and Prim's algorithm. Begin by moving the slider at the right to Kruskal's. I think first I have to hit play. Step 1, they take the shortest edge. Step 2, they take the next shortest edge. And then it's so on and so forth. Do you see kind of what they did? Let me reset and go again. So they take the shortest connection. Then they take the next shortest. We have a tree now. We've got to every vertice. There's no cycles, right? So we had to take the shortest. They just started taking all the shortests until they got to made sure every vertex was hit. If there was another short one, so this isn't a great example. Maybe there's, well, actually this is. Okay. So if you're looking at after 19, they picked 21, but 21 wasn't the shortest. 20 was. Yes, that it created a loop. It wasn't needed. Okay. You already had gone to that vertex. Don't need to go there. And Kruskal's algorithm does not require that we all start from one vertex and just go there. We could just put in AC because we knew that that was going to be the shortest way from A to C. So you'd connect to one of those two, and then that would connect between them. So this is Kruskal's algorithm. List the edges in order by weight, from smallest to largest. Begin choosing edges for the minimum spanning tree by selecting the edge with the smallest weight. If there is more than one with the smallest weight, choose any of them. Then select the next smallest edge with weight that does not create a cycle. If there is more than one option, choose any of them. Repeat step 3 until all the vertices are connected. That's actually not that hard, is it? Yeah, write this down. This is important. I'm going to pause the recording. Exam tip. A graph may have several minimum spanning trees. However, each one of them will have the same length. Okay? So you can define it however you want. It should have the same length. So we're going to look at this tree. The village is in a small region of the country. Use Kruskal's algorithm to determine the minimum spanning tree. So what is the first thing we're picking? Which is GF3. I'm going to draw that on there. What's the next smallest? AB4. then CE 5. Let's do BF, and then we'll do DF. Or, yeah, because those are not connected yet. And now we need CF. GD would be a cycle. So the reason I went to I jumped to CF going, I have, I looked over here and I went, I hit every vertex over here. I don't think of it as cycles. I think I have to connect every vertex in some way. And then I looked over at CE and I didn't have a connected vertex. I'm done. 7, 12, 19, 29.
Finally, English class together. Thank you.
Uh-huh. And we have the same minimum spanning tree. Oh, they got 36. Oh, I forgot a 7. I never wrote DF. I said it, but never wrote it. Okay, 36. Is your question quick, Keely? Okay. Exam tip. When building a minimum spanning tree, you have to show what you did. Okay. Which edges you picked in the order you picked them. Write it down. Do not just have an answer. So like we listed out our edges, that's good. Um, International mindedness, reliable access to electricity may be something you take for granted. However, according to the World Bank, more than 11% of the world's population still does not have access to electricity in 2017. That means 800 million people. Prim's algorithm is similar, so choose any vertex in the graph. Sometimes it'll be stated in the problem. In fact, most problems will say start at this and create a minimum spanning tree. Okay. Consider all adjacent vertices to the vertex in step 1. Choose one that has the lowest edge. Then consider all of adjacent vertices to the vertices already chosen. Okay, and then repeat, etc. That makes sense? So the graph below, again, same thing. Given that the power lines will begin in the village represented at A, use Prim's algorithm. Okay, so now we have to start at A. Maybe that's because there's a dam at A. Okay. So the minimum spanning tree might, well, I suppose it's still got everywhere. But we're going to go from A. So we start at A. Our minimum is AB, and that's 4. Then we're going, our next lowest one, AD is 16, BF is 7. FG is 3. And our next lowest, it looks like FD. FC. And they're going to look here. I think we're going to get the same minimum spanning tree that we had. CE is 5, 11, 14, 21, 31, 36. Okay. I'm going to pause and answer Mr. Klein's question. Okay, Prim's algorithm for adjacency tables. Go ahead and write this down. I'm going to pause the recording. Okay, so we're starting at A. This is my adjacency table for this graph. So we start at A, which means we cross out A and we write a 1 above the column. Why? Because we don't have to get to A. That's what the algorithm is. That's step 1. Step 2 is now I'm looking at A and I've got a 4 and a 16, so I'm going to circle my lowest one. And then I'm going to cross out B. This is the second place I went, so that I don't start going to B again.
Yeah.
Now I'm looking through B and I see a 7. So if I was writing this out, I'd probably write out AB. Then I'd write out BF. Now I'm looking at F. My next lowest one is 3. FG. So I'm going to cross out G. Now I can look at any of these. So from G, it's 9, but I've still got the 7. I can still look at, I'm looking for lowest between any of these that are in. That makes sense? FD, 7. Gotta cross out D. Now I'm looking at D is 5. D doesn't connect to anything. My next lowest looks like 10. So I've got the zeros here. The 5C is not in yet. E is not in yet. So it's 10 F C. And C. That makes sense.
Yes.
It's
Oh,
they had you cross out A because you're never going back to A. That's why you're crossing out these rows once you've been there. But you can look always from anything you've been to. I guess I should clear that. You'll see eventually they get to 36, just like we had before. Okay, for the exam, the edges in the list for the minimum spanning tree should be listed in order in which they were chosen by the algorithm. Very important. That's the end of the lesson. You have a 3.16 assignment. You can do some of them. There's a lesson tomorrow on the rest of 3.16.